Hi, my name is Riyadh Mansoor. I have a master's degree from Basra University in Iraq, and now I'm doing my PhD at Montfort University, Leicester, UK. Today I'm going to talk about the model optimization of vertically coupled micro-ring resonator-based filters, which is part of my research at Montfort. And this is the presentation outline. First, I will give the aims and objectives, the motivations. More talk will be on the ring resonator-based hydraulic filters as a component. Then I will explain the tools used for this work. Then I will wrap up with the conclusion and future. So first of all, the hydraulic filters are prone to crosstalk, result from insufficient separation of added and drop signal. And this results in two different types of crosstalk, intraband and interband crosstalk. We aim to increase the crosstalk separation. Therefore, we need to improve the signal integrity and reduce the bit error rate in the optical network. Our objective is to increase the bandwidth over which the crosstalk separation, high crosstalk separation is maintained. So we can increase the data rate in the system. Optical communication is an extremely fast growing technology driven mainly by the increased demand of the global expansion of the internet and in particular multimedia communication. So the future trend of optical communication has two directions. One, to increase the data rate for 10, 40, and 100 gigabits per second Ethernet. And the other direction, to decrease the size of the components. Before starting, I want to show this slide which explains the wavelength division multiplexing signal, 10 gigabit signal, 3 signals separated by 50 gigahertz. The drop signals from the filter are prone to two types of crosstalk. One is from the added signal with the same wavelength, and this we get decrease by increasing the crosstalk separation. This is called intraband crosstalk. The other type of crosstalk comes from the adjacent signals of different wavelengths, and this will be increased by increasing the out-of-band rejection ratio of the filter. Optical add-drop filter is a key component in an optical network. And among different types of optical add-drop filters, the ring resonator add-drop filter is of a great interest. It satisfies the requirement for decreasing the size of components. And in its simplest form, ring resonator add-drop filter consists of a ring waveguide coupled to two bus waveguides through the efficient modes of two waveguides. This is the frequency response of the ring resonator. So the resonance happens in multiple frequencies separated by frequency range called free spectral range, which is related to the radius of the ring resonator. General properties of ring resonator is the periodicity, as shown in this slide. So it is important for wavelength division multiplexing signal, and the small size of ring resonators, which is important for on-chip integration, and also a high quality factor for traveling electromagnetic energy. Generally, the coupling scheme of ring resonator two types. One is the lateral coupling, shown in the previous slide, which is the ring and two bus waveguides in the same plane. And in that scheme, the coupling, the dominant mode is TE mode. The other coupling scheme is the vertical coupling, which is of my interest in this talk. The ring and the waveguides are different plane, and the dominant mode is the TM mode. Here is the waveguides, and this is the ring. Here we have two parameters that affect the coupling coefficient, which is the vertical separation, D, and the lateral deviation between the centers of waveguides. In this direction is plus A, and this direction minus A. The advantage of vertical coupling over the lateral coupling shown in this slide, which is in the fabrication process, is more flexibility. The scattering loss is less in this type because the pulse waveguides are buried in the substrate silicon dioxide. And the most important for me in this work is it provides extra control for the coupling coefficient. That's clear from two parameters, which is D and A. Before talking on the result, I want to talk about the tools used in this work. We using the simulation software of CST Microwave Studio. CST is a 3D simulation engine, solves the Maxwell's equation in the ring resonator based on the finite integration technique, and also it provides optimization option depending on the thrust region optimization algorithm, and this is we tend to use it for crosstalk bandwidth maximization. We looking at the next step is to increase the crosstalk bandwidth. Okay, so using CST, we model ring resonator, silicon on insulator. So, ring radius was taken as 5 micrometer. The pulse waveguides from silicon with refractive index 3.47, buried in silicon dioxide substrate with refractive index 1.4. The cross section of pulse waveguides was chosen to ensure a single mode propagation TM mode. So it was taken as 0.34 micrometer width and 0.34 micrometer height. We start the optimization by first keeping the lateral deviation area as 0, so both the waveguides, tank waveguide and straight pulse waveguides, the same center. And we change the vertical deviation D, increase the deviation D to, and each time we measure the throw-port response, and draw-port response, and out-of-band rejection ratio. The crosstalk separation was measured by taking the difference between draw-port and throw-port response at resonance. And by keeping A equal to 0 and change the vertical separation D, we found that at D equal to 0.3 micrometer, the crosstalk was 20 dB, and then for this value of D, we kept D as 0.3 and changed A positive and negative. And found with A equal to -1 nanometer, the crosstalk separation increased to 25, and for these values of D and A, the out-of-band rejection ratio was found with -20 dB, which is sufficient to separate the interband crosstalk comes from the adjacent signals. To summarize, we were working on the vertical coupled ring resonator. We modeled the vertical coupled ring resonator. We tried to optimize the crosstalk separation, to increase the crosstalk separation by changing the coupling coefficients, by changing D and A. But the question here, to increase the crosstalk separation of 20 or 25 or more, what is the limit to increase the crosstalk separation? It was shown that the range between 20 and 25 is enough to ensure signal integrity at the receiver side. So our intention, our objective for the future work is to optimize the dimensions of radio resonator to increase the bandwidth over which the crosstalk separation in that range between 20 and 25 to ensure more bandwidth for high data rate filtering to fulfill the requirement for future optical communication. Thank you.
Questions, please. So you mentioned that TM mode allows you to control your coupling to the ring better than the TE mode. Could you comment on, for example, the maybe fabrication tolerances and reliability and maybe yield?
We are working now on most of our work on the optimization. So going to next step would be working on the fabrication. But usually with because of the vertical coupling, that's why we depend on TM mode in the vertical plane. That's why we more depend on the TM rather than TE, which is in the lateral plane.
Why do you think in the case of TM coupling you will have lower losses than TE?
That's what we goes in.
Did you show the results? Did you look at the results to compare between TE and TM losses?
TM, because the coupling mechanism to a ring and password, if you took in the same plane, the TE mode will be more because the coupling mechanism will be evasive mode.
If TE mode is very confined, again you will have
Same for
very low.
TE.
Yeah, so there is no advantage in this case.
No, same for TE. We depend on confinement of the leg. So with lateral, it's well confined and still there is coupling.
Right. Let us thank the speaker again.